Getting now to the crux of this module, and that is to describe the generation and propagation of an action potential. An action potential is the electrical impulse that travels along a neuron and is the mode by which the nervous system communicates. So an action potential begins with resting membrane potential. Once again, that is the difference in the electrical charge between the inside and the outside of a neuron when that neuron is at rest. At rest, this difference in electrical charge is minus 70 millivolts. So this means that the net charge of all of the ions inside the neuron is 70 millivolts more negative than the net charge of the ions on the outside of the neuron. On our figure, resting membrane potential is represented by a flat line like this, indicating that the state is relatively stable and that the membrane potential, or the difference in the electrical charge between the inside and the outside of the neuron, is approximately minus 70 millivolts. A graded potential then is a small deviation from resting membrane potential that makes the membrane either more polarized, which means that the inside of the neuron is more negative, or less polarized, which is when the inside of the neuron is less negative or more positive, but we say less negative because this value is still under zero. When the deviation makes the membrane less polarized or less negative inside the neuron, it is termed a depolarizing graded potential. When the deviation makes the membrane more polarized or more negative inside the neuron, it is termed a hyperpolarizing graded potential. A graded potential occurs when a stimulus causes either a mechanically gated or ligand-gated ion channel to open or close. These ion channels are located mostly in the dendrites of sensory neurons and the cell body of our other neurons. To say that these electrical signals are graded means that they vary in the amplitude or size, depending on the strength of the stimulus. So they are larger or smaller depending on how many mechanically or ligand-gated ion channels opened or closed, and for how long each of those channels remained open. The opening or closing of these ion channels will alter the flow of the ions coming across the membrane, producing a localized electric current. Now, although an individual graded potential only produces a small and short-lasting change in the membrane potential, graded potentials can become stronger and last longer by summating with other graded potentials. Summation is the process by which these graded potentials add together. So if two depolarizing graded potentials summate, like what we've got up in the slide here, the net result is a larger depolarizing graded potential. So we've got stimulus 1 and stimulus 2 here. They're both roughly equal in size or amplitude. When they occur close together, they will summate or add together, and the net result is a greater change in that membrane potential. Similarly, if we have two hyperpolarizing graded potentials summate, then the net result is a larger hyperpolarizing graded potential. If we have two equal but opposite graded potentials summate, then they will cancel each other out. Now we need summation to occur because a single stimulus and the opening of a single mechanically or ligand-gated ion channel is unlikely to reach the change in membrane potential that we need to trigger an action potential. This change in membrane potential, which then triggers an action potential, is what we call threshold. And that brings us to an action potential, which is a sequence of rapidly occurring events that decrease and reverse the membrane potential and then restore it back to its resting state. An action potential has several phases, which I'm going to need you to learn, which are determined by the ion channels that are opened and closed at the time and the resulting movement of ions. So as I'm sure you've gathered, An action potential begins with resting membrane potential. Resting membrane potential occurs when both the voltage-gated sodium and potassium channels, so for those who are unsure, sodium and potassium channels along the membrane of the neuron are closed. And for that reason, there is very little movement of ions into or out of the cell. That resting membrane potential is about minus 70 millivolts. Next, we have a series of graded potentials that will summate and reach threshold, which is this line here, this purple dashed line, and is about minus 55 millivolts. At threshold, voltage-gated sodium channels will open, and due to both the electrical and chemical gradients of sodium, sodium moves into the neuron. If summation of the graded potentials does not reach threshold, then those voltage-gated sodium channels remain shut and an action potential does not occur. So this happens even if the graded potential reaches just up under this line, even if that graded potential reaches minus 56 millivolts. The voltage-gated sodium channels will not open and an action potential will not occur. So this is what we call the all or none principle of an action potential. Either the graded potential reaches threshold or it does not. So as I said, once those graded potentials reach or surpass threshold, our voltage-gated sodium channels open and sodium moves into the cell. That influx of sodium ions causes the membrane potential to go from minus 50 millivolts to positive 30 millivolts. It does this because our sodium ions are positively charged. So positively charged sodium ions are now coming into the cell, which makes the net electric charge of the ions inside the neuron more positive than the net electric charge of the ions on the outside of the neuron. Now, with depolarization, even with a really big stimulus that causes a membrane potential to far exceed threshold, the amplitude or the max amplitude or size of an action potential will not change. So once the graded potential reaches threshold and our voltage-gated sodium channels open, they're open. There's nothing else they can do. So you can kind of think of this like pushing over the first domino when you line up all the dominoes in a row. So once there's enough force to push that first one over, then all of them will fall. It doesn't matter if you push that first one really, really hard, the same effect is going to happen. They're all going to slowly, in order, fall over. The next phase of an action potential is then repolarization. So this occurs when the voltage-gated sodium channels become inactivated. So they've been closed, they've been open, and then now they're inactivated. And sodium can no longer move into the cell. At the same time, voltage-gated potassium channels will open. And again, due to both the electrical and chemical gradients, potassium starts to move out of the cell. So with no more incoming positively charged sodium ions and increasing amounts of positively charged potassium ions leaving the cell, the membrane potential goes from that positive 30 millivolts back down to our minus 70 millivolts. The final phase is then hyperpolarization. So during this phase, the voltage-gated sodium channels are now closed, but the voltage-gated potassium channels are still open. So because we have those positively charged potassium ions continuing to exit the cell, that membrane potential drops below resting membrane potential to about minus 90 millivolts. In time, our voltage-gated potassium channels will then shut, meaning both sodium and potassium ion channels are closed and there is little movement of ion. During this phase, the sodium and potassium pumps then begin to restore our resting membrane potential by transporting sodium from the inside of the cell back to the outside of the cell, and potassium ions from the outside of the cell back inside of the cell. So we get that restoration of the resting membrane potential. Now, within the period or the time frame of an action potential, there are two phases which we call refractory periods. A refractory period is the period of time after the initiation of an action potential that a second action potential cannot be generated. The absolute refractory period is the period of time that even with a really strong stimulus, a second action potential cannot be generated. The absolute refractory period occurs between the start of depolarization and the end of repolarization, because during this time, the voltage-gated sodium channels are either already open and therefore can't be opened further, or they are inactivated and so therefore must first close before they can be reopened again. So during this time, nothing is going to reopen those voltage-gated sodium channels. So no matter what, another action potential cannot be generated. The relative refractory period is then the period of time during which a second action potential can be generated, but only by a larger than normal stimulus. So the relative refractory period coincides with hyperpolarization, which is when the potassium channels are still open and potassium is leaving the cell, causing this membrane potential to become even more negative, so below our resting membrane potential. Because this membrane potential is now further away from threshold than at resting membrane potential, that is why a larger than normal stimulus is required to generate that second action potential. Lastly, to communicate information from one part of the body to another, action potentials in a neuron must travel from where they arise to the axon terminals to connect with another neuron, a muscle, or a gland. How an action potential moves along a neuron is called propagation. So when a part of the axon in a neuron is depolarized to threshold, the voltage-gated sodium channels in that region open and the sodium rushes into the cell. That influx of sodium changes the membrane potential in the regions of the neuron adjacent to the initial site of depolarization. In response, the voltage-gated sodium channels in those regions then begin to open, and so on and so on. And that's how an action potential spreads or propagates along a neuron. However, it's important that an action potential moves only in one direction, so that the electrical impulse and the information that we're sending travels the way that we want it to. And this is where our refractory periods become important. So if we take a look at this image here, let's look at this first line here. And this is part of the axon. In this region here, our greater potentials have summated and reached threshold. Our voltage-gated sodium channels are open and sodium is now coming into the cell. These positively charged sodium ions are going to spread out to either side of that initial site of depolarization. If we look down here now, on this side, so as the ions have spread, on this side, the sodium ions will change the membrane potential and it will open up more voltage-gated sodium channels. So more sodium can come in and spread out, and that action potential will move along the axon. However, on the other side of that initial site of depolarization, even though the sodium ions are moving to that region of the neuron, because the action potential has just come from this space, our voltage-gated sodium channels are now inactivated or in that absolute refractory period, which means even though there's incoming sodium and the membrane potential should change, they cannot be opened again, and so the influx of sodium ions does nothing at this site. This process will then continue to work its way along the neuron, propagating that action potential to the axon terminals. Now, there are two different types of propagation of an action potential down a neuron. We have continuous propagation and saltatory propagation. Continuous propagation is the method of propagation which I just described, which involves the step-by-step depolarization and repolarization of each adjacent segment of the plasma membrane. So first, here we'll depolarize, the neurons come in and spread out, that depolarizes this section and then this section, and it slowly moves its way along that neuron. This type of propagation is slower than saltatory propagation, as every little segment of that axon has to undergo this depolarization and repolarization process. Continuous propagation occurs only in axons that are unmyelinated, which means there's no myelin surrounding the axon. This type of propagation also occurs in our muscle cells. Saltatory propagation is the other type of propagation that occurs in neurons that have myelinated axons. So it's got myelin, or a fatty protein covering surrounding the axon. Here, voltage-gated ion channels are only found in the nodes of Ranvier. So the nodes of Ranvier are these little gaps between the myelin. If these red bits are the myelin, these gaps are the nodes of Ranvier. And in those nodes of Ranvier are where we find those voltage-gated sodium and potassium channels. So when these regions, or let's start here, when these regions of the axon are depolarized to threshold, those voltage-gated sodium channels open and sodium rushes into the cell. Now, the sodium will flow through the cytosol. It throws through this region here because it's all encased by the myelin to the next node of Ranvier. Here, it will cause that change in membrane potential, which opens up our next lot of voltage-gated sodium channels. The sodium rushes in, that sodium spreads out past that myelin through the axon here, and then opens up the next section. So because of the myelin, the depolarization does not need to happen at every single little segment of the axon. Rather, it can kind of leap or jump between sections, and SALTA actually refers to leaping between those nodes of Ranvier. Now, because of this method of propagation is much faster, but it can obviously only occur in axons that are myelinated. Now, a few factors which influence the speed at which an action potential will propagate or travel along a neuron. These include whether an axon is myelinated, which we've just spoken about, the diameter of an axon. So if an axon it has a greater diameter, there's a larger surface area, so therefore there's more voltage-gated ion channels, so more of the sodium can come into the cell. And then also the temperature. So action potentials will propagate faster when a cell is warm than when it is cold. Now, I know that was a lot of information, a lot of new terms, but understanding how action potentials work are not only important for this module, but also this unit and a lot of the units that you will go on to partake in. So as a bit of a recap, an action potential begins with resting membrane potential, which is the difference in the net electric charge of the ions inside of the neuron compared to outside of the neuron. At rest, this is about minus 70 millivolts. A stimulus will then cause the opening of either a mechanically gated or ligand-gated ion channel, which will cause either a depolarizing or a hyperpolarizing graded potential, which brings the membrane either closer or further away from threshold. Threshold is this line here, which is the change in membrane potential that must be reached for our voltage-gated sodium channels to open and for an action potential to occur. The first phase of an action potential is then depolarization. So as I said, this is where the voltage-gated sodium channels have opened. Our positively charged sodium ions are moving into the cell, which makes our membrane potential more positive. Then we have repolarization. So this is where our voltage-gated sodium channels are inactivated, but our voltage-gated potassium channels have now opened. So the positively charged sodium ions have stopped coming into the cell. The positively charged potassium ions are starting to leave the cell. This causes the membrane potential to become more negative. Lastly, we have hyperpolarization, which is where the potassium channels stay open. Our potassium continues to exit the cell, making this membrane potential even more negative. We then have the potassium channel shut, potassium stops exiting the cell, and resting membrane is restored by the work of our sodium and potassium pumps. This phase here of our action potential is also called the absolute refractory period, because during this time a second action potential cannot be generated because our voltage-gated sodium channels are either already open or they're inactivated. So a change in membrane potential is going to do nothing to them. This phase along here is then our relative refractory period, which is when a second action potential can be generated, but only by a larger than normal stimulus. This is because the voltage-gated sodium channels are now closed, so they can be reopened in response to a change in membrane potential. However, because of this outflux of our potassium ions, that membrane potential has actually gone below resting membrane potential. It's further away from threshold, and therefore a larger than normal stimulus is required to actually reach this threshold level. Lastly, the two types of propagation, or the way in which an action potential travels along a neuron, is continuous propagation or conduction and saltatory propagation or conduction. In our continuous conduction, this occurs only in our unmyelinated axons and our muscles, where each little segment of the axon must be depolarized for that action potential to move along the axon. In our saltatory propagation or conduction, the action potential can leap between those nodes of Ranvier. So it is a much faster process, but only occurs when that myelin is present.